So the difference between MergeSort and QuickSort. We'll start with an example, which is a satirical illustration contrasting two corporate employees archetypes using computer science algorithms as metaphors for their workplace performance and stability. On the left, the QuickSort employee is depicted as chaotic, stressed, and volatile with messy hair and disorganized papers. He is associated with a high performance risk in the worst case scenario, um, n to the power 2, the time complexity, despite having good average case results. A red warning icon highlights this instability. On the right, the merge sort employee is calm, organized, and confident, holding a coffee cup and reviewing a structured clipboard labeled office politics. He is associated with stable, predictable performance, dollar and n log n. So, regardless of the situation, and maintains consistent terms with the manager. So the illustration uses a split composition to directly compare their differing approaches to corporate work and stability. MergeSort is a divide and conquer algorithm. The base case is a subarray with 0 or 1 element. We merge by comparing front elements, choosing the smaller each time. On the right side, we repeat the process. Finally, we merge these two sorted halves. Compare 1 and 2, pick 1, compare 3 and 2, pick 2, compare 3 and 4, pick 3, pick 4. Merge sort's heart is the merge operation. So this is how merging works. We take two sorted arrays left and right, compare elements, pick the smaller and move pointers, copy all the remaining elements. The merge phase step by step reconstruction. We begin with 8 individual sorted lists, each containing a single number. Step 1, merging pair of single elements. The first step in reconstruction is to take the isolated elements and merge them into sorted pairs. 8 and 3 to form 3. 1 and 7 merge to form 1, 7. 2 and 5 merge to form 2, 5. 4 and 6 merge to form 4, 6. The image below visualizes these four simultaneous merges. Note the connecting lines showing the flow of elements into their new sorted structures. Step 2, merging sorted 2 element list. We now have 4 sorted lists, each of length 2. The next steps to merge these into 2 sorted lists of length 4. 3, 8 and 1, 7 are compared and merged. 1 is smaller than 3, then 3 is smaller than 7, then 7 is smaller than 8, resulting in 1, 3, 7, 8, 2, 5. And 4, 6 are compared and merged. So the resulting sorted array is 2, 4, 5, 6. The visualization below shows this transition. The input blocks now match the output of step 1, the 3, 8 and 7 and 1, 7 pairs, and the arrows demonstrate how they combine into the new larger sorted 4 element arrays. Step 3, the final merge. We have reached the final merge. We now have two sorted lists of length 4, left list 1, 3, 7, 8, right list 2, 4, 5, 6. The final merge operation compares the front elements of both lists and moves the smaller elements into the final array. So compare 1L and 2 and move 1. So compare 3L and 2, move 2. Compare 3L and 4, move 3. Compare 7L and 4, move 4. Compare 7L and 5, move 5. Compare 7L and 6, move 6. The right list is exhausted. Move the remaining elements from the left list 7, 8. The final image shows this process. The inputs are the two 4 element arrays from step 2. The arrows demonstrate them combining into a single contiguous 8 cell block containing the fully sorted array. Sure, I implement merge sort with two functions, merge sort and merge. Merge sort handles the recursion. It checks the base case left equal right, computes a mid, recursively sorts the left and right halves, and then calls merge on them. In merge, I create two temporary arrays for the left and right halves, copy the data, and then merge them back into the original array using 3 indices. I compare the current elements from each half, place the smaller into the main array, and move the pointer. Finally, I copy any remaining elements plus 1. This merge procedure takes linear time in the size of the two halves, and because we have 0 we have n log n levels of recursion total time its own loan. So the algorithm is stable and needs on extra space due to the temporary arrays. One base case. This is the stop condition. The algorithm checks if left equals right. If the current range has 0 or 1 elements, it is already sorted by definition. This prevents the function from attempting to split an already sorted segment. To divide midpoint calculation. To split the array, the algorithm calculates the center point using mid equals left plus right, left divided by 2. Why this formula? It is mathematically equivalent to left plus right slash 2, but it is safer. So it prevents integer overflow which can occur in programming when adding two very large index numbers together. So 3 divide and conquer recursion. The algorithm uses recursion to repeat the splitting process. It creates a tree-like structure repeatedly calling itself on the left half left mid I and the right half mid plus 1 right. This continues until the array is broken down into its smaller possible units, individual elements. And number 4 is merge. Once the smaller units are reached, the algorithm begins the conquer phase. It calls the merge function to combine these tiny sorted segments back together. As the stack unwinds, it compares elements from the two halves and reconstructs the array in the correct sorted order until the entire sequence is complete. Merge sort is technically a top down algorithm when it comes to dividing the problem, but it is considered bottom up when it comes to solving and building the solution. So, here this is a breakdown of why the bottom up description is accurate for the merging phase. One, the recursive unwinding. The recursion starts by splitting the array repeatedly, the top down approach. However, the computer cannot finish a parent function call until its child function call, the smaller segments, are complete. So, therefore, the work happens in reverse order of the calls. The base cases, the absolute bottom of the tree consisting of 0 or 1 elements, are the first to be finished and returned. Once these are returned, the merge function executes. Quicksort recursion works by choosing a pivot, partitioning the array around it, and then recursively sorting the left and right parts. The recursion stops when a subarray has 0 or 1 element because that is already sorted. A simple way to picture it is this: pick one element as a pivot, move all smaller elements to the left and all larger elements to the right. Call quicksort again on the left side and the right side. Keep repeating until the pieces become too small to split. The important difference from merge sort is that quicksort does its rearranging during the recursive step itself, not afterward. So, in interview terms, you can say quicksort recursion sorts by partitioning around pivots and then recursing on the two partitions. So, quicksorts call the top-down recursion because it starts with a full array, picks a pivot, partitions the array, and then recursively works on the smaller subarrays. The problem is broken from a big whole into smaller parts first, which is the defining pattern of top down recursion. A simple way to say it in an interview is quicksort begins with a complete problem and recursively divides it into smaller subproblems using partitioning. So the recursion flows from the top level down to the base cases. Quicksort time complexity is O n log n on average and in the best case, but it can drop to O n square in the worst case. So when the pivot splits the array very unevenly, easy meaning best case, the pivot splits the array into two equal halves, so the recursion stays balanced. Average case, the splits are usually decent, so quicksort stays fast. Worst case, the pivot is always the smallest or largest element. So one side gets almost everything and the other side gets almost nothing. Simple memory trick: good pivot, fast about O n log n. Bad pivot, slow about O n square.